In this video, we're going to take a look at Le Chatelier's principle and how it applies to equilibrium systems. So what Le Chatelier's principle basically states is that anytime a stress is applied to an equilibrium system, the system will act in a way to alleviate that stress. So it will counter whatever is done to it. So we're going to take a look at how that applies to temperature changes, the presence of catalysts, changes in concentration, as well as the changes in pressure for gaseous systems only. So first we'll take a look at temperature. So here we have a reaction where N2O4, which is a colorless gas, converts into NO2. And you can see here that at lower temperatures, you have a higher presence of the colorless reactant than you do the dark brown product. And at higher temperatures, you have a higher ratio of dark brown product to the colorless reactant. And you can see here that this reaction is an endothermic process because heat is listed as a reactant. So if you think of heat energy as being a reactant in this case, when you add heat, you're increasing the amount of reactants, so it's going to have to convert some of your reactants into products in order to counter that stress applied to it. So if we take a look at that quantitatively here, you can see that the K for this reaction, which again is ratio of product concentration over reactant concentration, and you account for the coefficients from the reaction as exponents. You can see here that at a lower temperature, you have a much lower ratio of product concentration to reactant concentration than you do at high temperatures. And again, this is because it's an endothermic process, and you can think of adding heat as a reactant, which will push to making more product. If the reaction was exothermic, where heat was listed as a product, then if you heated it up, it would favor the reverse reaction, or some of your product would convert back into reactant. Catalysts actually don't impact the equilibrium ratio that you have. So you'll have the same ratio of products to reactants as you would with no catalyst present. All it does is impact how fast you get there. Concentration changes we can quantify as a K versus Q situation, which there's a separate video on. And essentially what this does is whenever you increase the amount of a reactant you have, you're going to favor the production of more product because you basically have perturbed the equilibrium or knocked it out of whack. If you add a product, it's going to convert back to a reactant. If you remove a reactant, it's going to have to make more of that reactant to get you back to that K value. But none of these changes affect K. It only affects the position of the equilibrium, which we would call Q. So let's continue on with that and look at the reaction or the interconversion of butane and isobutane, where we're considering isobutane as the product. At equilibrium, you should have a ratio of these two things of 2.5 isobutane for every butane concentration equivalent. So at equilibrium, you could have 1.25 molar isobutane and 0.5 molar butane. That would give you a K value of 2.5. But what if we add some reactant? Well, then we're not at equilibrium anymore, and we're not going to have that same ratio. So we're going to look at that as Q. So Q is the ratio of product to reactant concentrations at any point in time. So if we plug those values in here, you have 1.25 molar isobutane still, but you've increased the butane concentration to 2. And so that gives you a value of 0.63, which is substantially less than the 2.5. So since Q is less than K, you're going to have more of the reactant convert to product. So some of your butane is going to convert itself to isobutane. And we're going to take a look at what that looks like mathematically. So what we can do is set up a rice table. This should say reaction here, where you have the initial concentrations, you have the change that's going to go on, and you have your equilibrium concentration. So in this case, we know that however much butane gets lost is going to be equal to the amount of isobutane gained. And since we're trying to figure out what that value is, we're going to represent it with the letter X. So at equilibrium, we're going to have the 2.00 molar concentration of butane that we initially had, and we're going to subtract X from that. And the amount of isobutane we have is 1.25 plus X, because that's the concentration that's going to be added to that. So we know that at equilibrium, K is equal to 2.5. And that's our ratio of isobutane to butane. So what we do is we plug in our concentrations that we use to represent those values, and we essentially just solve for X. And when we do that, we see that X is 1.07. So you could quantify how much conversion there will be. So in this case, the amount of butane will go from, the concentration of butane will go from 2 to 0.93 as it loses 1.07. And the isobutane will jump up to 2.32, and you'll see that that actually reestablishes the ratio of 2.5 to 1. So if you divide 2.32, the molar concentration of isobutane, by 0.93, which is your concentration of butane, you would get back to the equilibrium constant. So again, changing the concentration doesn't change K, it just changes where you are at that point in time, and you have to look at whether or not your Q value is less than K or greater than K. If it's less than K, you're going to make more product to get back to that higher ratio. If Q is greater than K, then you have too high of a product concentration at that point in time, so it's going to have to convert back to more reactant. And lastly, we're going to look at the effects of pressure on gaseous equilibrium systems. So here's a generic reaction of A plus 2B gives you C. And all of these are in the gaseous phase. So let's say at equilibrium, all the concentrations for all species are 2 molar. Now again, things don't have to be at this, the products and reactants don't have to be at the same concentrations to be at equilibrium. I just picked the number 2 for something you can easily see the calculation where the numbers come from. So if we established a K for this system, you would see that when you plug in all the values, you get a K of 1 to 4, or 0.25. So let's say we double the pressure of this system. In order to do that without adding any moles of gas, we're going to cut the volume in half. So if you cut the volume in half, all of the molarities of these gases are going to double. So since molarity is moles per liter, when you cut the volume in half, the concentration doubles. So let's take a look at what that does to Q. So now all our molarities have gone from 2 to 4, and when we plug that into the Q expression, which is the same thing as K, again, it just represents your equilibrium expression just at any point in time, you can see that you get a value of 1/16, which is substantially less than K. So what's going to happen is the reaction will shift forward to reestablish K. However, I want to point out that K never changed. Okay, it just made it so that you had to make more product to get back to its K value.